Good evening. I am Tania Guzman Silva from the Photocatalysis and Nanobiotechnology Laboratory of the Universidad Autónoma de Querétaro, Mexico, and today I will be presenting the poster for my undergrad thesis titled Photovoltaic Properties of Titanium Dioxide/Zirconium Dioxide Solar Cells by the Sol-Gel Method. The abstract reads, bettering the energy conversion rate of dye-sensitized solar cells, or DCSS, can be achieved with a layering of titanium dioxide on top of the microporous silicon dioxide. Research has focused on how to further improve the titanium dioxide dye-synthesized solar cells by using different doping agents and combinations with other nanomaterials. Zirconium dioxide has become an attractive option to use in combination with titanium dioxide because it reduces the loss of recombination in the electron-hole recombination interface, and it also increases the surface area of the thin film, allowing for more surface area for the electron transference, which overall improves the energy conversion efficiency. The current work presents the photovoltaic properties of a titanium dioxide/zirconium dioxide solar cell prepared by the Sol-Gel synthesization, and the characterization of the thin films by both the dip coating and the spin coating methods. Titanium dioxide is an extensively researched nanomaterial with photovoltaic and photocatalytic applications. It is attractive because of its abundance as well as its high chemical stability and resistance to corrosion. Titanium dioxide in its anatase phase, seen in figure 1, is used as a semiconductor due to its long-term stability and good photovoltaic and photocatalytic activity. For the effective photoexcitation of the titanium dioxide in the anatase phase, illumination needs to be higher than the bandgap energy of around 3.2 electron volts. It has an absorption threshold of around 380 nanometers, where around 5% of the ultraviolet fraction of solar radiation is active. Because of this, the use and effects of titanium dioxide in dye-sensitized solar cells has been widely explored and reported. The doping of it improves the photovoltaic behavior of silicon dioxide cells, especially when it is combined with other nanomaterials. Zirconium dioxide is an attractive option for this because of the high thermal stability, strength and durability of its monoclinic phase, which can be seen in figure 2. Its optical and photoluminescent properties make it an atypical photon absorber. By layering the zirconium dioxide on the surface of the titanium dioxide films, a larger surface area is generated at a lower temperature, which allows for a greater physical absorption in the surface of the solid. A larger surface area means that photoelectrons are recollected in a larger number of wavelengths. This reduces the recombination loss at the electron-hole recombination interface between the titanium dioxide layer and the dye of the cell. This leads to an increase of energy conversion rate efficiency, which is exactly what scientists are looking for. There are various methods to synthesize these solar cells, but Sol-Gel is often used because of the surface and texture of the thin films generated by this method, which allows for great uniformity of samples. Sol-Gel consists in the formulation of a solution from a precursor substance mixed with an acid to modify the metal ion. As seen in figures 3 and 5, the zirconium dioxide sol was created by mixing zirconium 4-propoxide with nitric acid and ethanol for an hour, while the titanium dioxide sol was generated from a titanium 4 isopropoxide with 2-propanol and hydrochloric acid, diluted with deionized water. After the solution was done, the thin films were placed in glass substrates using the dip coating and spin coating equipment in the lab. Figure 4 shows the immersor use. Different immersion speeds and spin speeds were used. Temperature and time of the heat treatments were utilized and varied, as well as different number total of layers and temperatures for the final calcination process. Figure 6 is a picture of the zirconium dioxide thin film obtained in the lab. These thin films were characterized by X-ray diffraction to determine the degree of crystallinity and the crystalline structure obtained from the diffraction patterns of the samples. Ultraviolet by visible spectroscopy was also carried out to obtain information about the electronic state of films and their bandgap energy. The best combination of parameters will be used in following months of research to further test the photovoltaic properties of the synthesized nanomaterials. In conclusion, titanium dioxide and zirconium dioxide thin films are used to improve the energy conversion rate and overall efficiency of the dye-sensitized solar cells. While zirconium dioxide improves the absorption rate due to its optical properties, titanium dioxide broadens the range of wavelengths of solar light that the cell can collect. A combination of both of these increases the energy conversion efficiency significantly, due to the zirconium dioxide layer providing the titanium dioxide with more surface area to collect photoelectrons, effectively increasing their recombination time and transference and transference of electrons. The sol-gel method allows for the synthesization of very stable crystalline structures. This is shown when the films are characterized by X-ray diffraction and ultraviolet visible spectroscopy. For these reasons, more research should be made into the titanium dioxide/zirconium dioxide layer films in dye-synthesized solar cells. The researchers would like to thank the Photocatalysis and Nanobiotechnology Laboratory and the Engineering Faculty of the Universidad Autónoma de Querétaro for their support and guidance during the development of this project. I thank the audience for their time and attention.